So I hesitated to make this video. There's a massive number of resources available on the central limit theorem. A YouTube search, a Google search, there are some really quality resources that exist. And so I didn't feel the need to reiterate those verbatim. This video is really just been more for my BA 254 students as a way to, I guess, personalize the central limit theorem, and at least you can hear the summary version from me. But the central limit theorem is massively important for us as statisticians. Alexander Holmes puts it, the central limit theorem is one of the most powerful and useful ideas of all statistics. As we will see in this section, this powerful theorem will determine just what we can and cannot say in inferential statistics. Those are pretty massive, strong statements to make. Put another way, Charles Whelan put the central limit theorem, which is the LeBron James of statistics. If LeBron James were also a supermodel, a Harvard professor, and the winner of the Nobel Prize. Pretty powerful statement. I tend to agree, maybe not with all of those things, but I love the passion that Mr. Whelan shows us in that quote from his book, Naked Statistics. But I guess as a point to start, again, to personalize this for my BA 254 students, the central limit theorem is just fundamentally in a really important part of what we're going to do within statistics, especially when you look at the type of data that we're going to use as business people, right? So we're going to use these measurable, large, hopefully sample values, right? Especially that have been dollarized or put into some kind of monetary value. All right. So when we look at the central limit theorem, what the central limit theorem says is it says basically for large random samples, the shape of the sampling distribution of the sample mean is approximately a normal distribution, extremely close over a large sample size, right? So what we also find is the central limit theorem holds, it's more accurate as our sample size goes up, all right, than when our sample size is low, all right? And of course, it stands to reason if it's a normal, if the population is inherently normal, when you sample it with your sample distribution, or sample it over and over again, you're also going to be left with a normal distribution. What that tells us is we can look at all kinds of different types of shapes of distributions. We can go in and just have some crazy types of distributions as long as they're continuous. What happens is as we go in over and over in terms of the number of samples, as we start to look at what that distribution of those sample values looks like, again, it's going to start to look like a picture that we're going to grow increasingly familiar with. It's going to look like a normal distribution. What we can do then is apply a lot of the stuff that we looked at prior in terms of the mechanics of dealing with these normal distributions in a lot of different cases. Now, as we get into normal probability distributions, we have to establish the guidelines for when we believe that we can actually go in and say that a distribution is normal. The best way to do this is to start to look at an hypothesis test and say that this shape is valid because we can go in and actually run a hypothesis test and figure out is the frequency in which values appear going to help us look like a normal distribution. Okay, so there are tests that we could do for normality that basically, again, are going to say, does this distribution, is it a valid assumption to make? For now, before we get into that, we're going to use kind of a guideline. And we're going to say that we're going to employ the central limit theorem. Now, bear in mind, we're still really early on in our introductory statistics world. We're going to say we're going to employ the central limit theorem if our sample size is greater than or equal to 30. If our sample size is less than 30, we're not going to say that we can make this bridge, all right, from looking at this distribution of these sample values. That is not a overly scientific way of looking at the employment of the central limit theorem. I could go into some examples in a previous life when I kind of had a real job that would never be good enough for my customers to employ certain assumptions into the analysis that I did. But as a starting point, it's a pretty good kind of standard that we can hold ourselves to say that we're going to employ the central limit theorem again when our sample size is greater than or equal to 30. Again, it's not perfect, but at least in these introductory stages, it gives us kind of some rules of the road, for lack of a better way, some standards at which we can apply. And then as we develop, our understanding of how we can validate this kind of an assumption later, we can apply better tools. All right. So I would also, I guess, end this video by encouraging you, as exciting as it sounds, to go out and do some independent research on the central limit theorem. Again, there is just a massive amount of resources that exist for that. In the next video, what I'm going to do is start getting into some very specific applications of the central limit theorem and how we can start to find probabilities with these set of assumptions and these types of probability scenarios.